Hey guys, we're looking at our Chapter 11 worksheet right now on being able to figure out how to do a goodness of fit test. We should notice that you're supposed to take one sample and ask one question. Here, our one sample is a bag of M&Ms or a random sample of 1,292 M&Ms. Hopefully that's more than a bag. And we're taking the color of each candy, so that's our one variable that we're measuring. And we're trying to check to see if it matches previous data. See how we're trying to see, does it match what was published on a website? If that's true, that's our goodness of fit test. All right, so we'll start by defining that population parameter. In this case, it's a proportion. So we're looking at the probability that each color is what they say. So P sub color is the true proportion of each color. Okay. I guess I might want to say of each M&M. Okay. Your hoe is that the P sub each one, so P sub blue is 24%. P sub brown is 13. Okay, so I think I got each color. 1, 2, 3, 4, 5, 6. All right, there's 6 colors with 6 categories. Our ha is just at least one of those is incorrect. So the data on the website is not true. Okay. As we go through then and try to check our assumptions first and foremost is that it was a random sample. So the random condition is met. Since it was stated. And there's a fairly large sample of M&Ms. Our independence condition is met. Since the population is large. Our little 10% rule. We can sample without replacement. And so each individual candy that we choose isn't going to change the color of the other candies chosen. All right. Our last condition should be our expected count. So we're going to do that in our table. We have our sample size, right? N is what was given. And to find our expected counts, you're supposed to multiply your sample size times each percent. So those percents that were given to us over in our data here is showing up for our null hypothesis. So for our first one, for red, you're going to multiply the probability times its expected in that count. It's going to come out to be a decimal answer. And so you are multiplying like each probability times the sample size. And you don't have to show each one of these multiplied out like that, but at least write what they are. When you add up all of the expected counts, you should get the same as the sample size. Okay, all of those are at least 5. So the large counts condition is met. And you can tell them to see the table for those expected counts. All right, now we're going to go through and you would need to type stuff into your list. So remember, in your calculator, you're going to go through and you're going to put all of these observed into list 1. And then in list 2, you're going to put all of these expected counts. And if your calculator has it, you can do the goodness of fit test. That's the kind of test that we want to do. So we'd have our chi-squared goodness of fit test. If your calculator doesn't have that test, you're going to have to calculate this by hand. So that test statistic is supposed to be our observed minus its expected squared divided by the expected. And then you would add together the next one in our list, what we observed minus what we expected. Oops, that's not what we expected. Divided by what we expected. It's a 0. Okay, and we can show our work that way. I guess I didn't need an ellipse there because that was the second one. The last one for blue, we observed minus we expected. Okay, and so once you do all that, you get a chi-squared test statistic of 43.01. We want to put our degrees of freedom on here. There were 6 colors, so our degrees of freedom should be 5. Also, our alpha or significance level for this problem was 10%. So if we are looking at our chi-squared distributions, remember they're always skewed right. And so when we're saying we landed here at 43, that's quite a bit of ways away from 0. How much area is in that tail? How probable is it to see something this extreme or higher if our null hypothesis is true? Well, then we want to calculate that p-value, and our p-value would be the probability of a chi-squared value greater than 43 on this degrees of freedom curve. And you can do chi-squared CDF in your calculator. You would need the lower bound to be your test statistic. Your upper bound would be infinity, and then it'll ask you for the degrees of freedom. If you did the test in your calculator, you get a 3.6813 times 10 to the negative 8 value, which is about 0 if you're using the table. That p-value is very low, so then it comes to our conclusion. Since our p-value is less than our alpha at 10%, we should reject HO. Okay, so if we go back and look at, we've now rejected that they're all what they said they were. We have support then for this alternative hypothesis. So we're going to support that at least one of those colors is incorrect. Okay. All right. We'll do the next one in a minute.